All right, again, good morning and good afternoon to everybody. As I said, my name is Svanjar Kuhi, Simulation Product Manager at Intercad, and today's topic we're talking about SolidWorks flow simulation, and we're specifically going to the turbomachinery analysis and find out what we can do with SolidWorks flow simulation. The objectives, we are going about a review on turbomachinery definition and classifications. We're looking at the components of the turbomachineries and also the power generation, let's say, procedure. We will highlight the design procedure and trends. Well, these are the achievements we want in any single, let's say, turbomachinery. And then be shifting on CFD, computational fluid dynamic in turbomachinery, and how we can use this powerful tool to achieve our goals. Before we go into our, let's say, practical examples, we will introduce a concept of rotating reference frames and its application in CFD turbomachinery. We will expand it and explaining how it can be done in the SolidWorks flow simulation, and practically we will go for two case studies, one more in detail as case study 1. We're talking about analysis of centrifugal pump assembly. And then we're going to the more complex one, not going into all details, but just looking at the result, which is about mixing tank assembly, and we're using different scheme of turbomachinery. All right, let's move. And the first thing we have to say, what is a turbomachine, which is a device as energy is transferred to or from a continuously flowing fluid through a casing by a dynamic action of a rotor. So basically we have mass flow in and we have mass flow out. Now depends on the type of the let's say turbomachine we have energy interaction, either we extract it or we adding to it. So this dynamic let's say interaction between the fluid and the device is basically producing work or generating energy or adding energy to it. Okay, so based on this simple concept, we can divide our turbomachines by first energy conversion, which we have work absorber components such as compressor, fans, or pumps, or the other types which they are adding work such as turbines. Also, we can have a division by fluid type. Like most of the liquids, we can say they are compressible liquids, and some application of the gases could be incompressible, and you specifically know that we're talking about air jets and air pumps and jet pumps and these kind of let's say devices. The third category could be based on the fluid flow directions. So if we have axial flow in and out, or we have axial flow in and radial flow out, or we can have a mix of both axial and radial in our turbomachine. And the last type is about its physical action, either it's impulse turbomachines or reaction ones. Let's have a better look. We said the first division is about energy conversion. We have some devices such as a pump and compressor where you have the flow in, you are consuming power, and you add it to the fluid. So as you can see, pump is the very best or a very good example of that one. However, there are so many other let's say devices such as fan, blowers, compressors, and etc. which doing the same work. So we have work in added to the fluid. And the other type is power producing. Well, you have energetic fluid and it is coming to your device such as a turbine, and there are different, let's say, section in this device which is extracting the energy and make it work out. The second division, as we said, is talking about fluid type. Well, most of the hydraulic fluid machineries are nearly incompressible fluid, but we have no significant change in fluid density. So very good examples of those ones are centrifugal pumps, turbo pumps, or centrifugal fan in a lower RPMs. Well, it is not making even air as a compressible fluid active there. There are so many exceptions we can say when we're saying there is no thermodynamical properties change. It could be a cavitation as a part of it, but we are talking about in general terms. However, in the second division, we're talking about thermal turbomachinery, such as, well, we have compressible fluid, and then we have significant change on thermodynamical properties of the fluid. As you can see in a picture, the very good example of this is turbofan or jet engines. Well, we have different sections there, and we are significantly, let's say, changing pressure, velocities, maybe changing even the phase of the fluid if we're talking about, for example, steam. All right, now let's move to the next category. Well, we talked about fluid flow pathways. As we said, the first category is axial flow. Well, mainly or wholly, let's say, parallel to the axis of the rotation. So we have fluid inlet and outlet are in line and interacting with the power absorber or power adding section. Well, one is very important thing is always we can have an analysis to the vectors of the velocity and how it's interacting with the power, let's say, absorbing section. And this is something analytically you're always using to get the efficiencies, finding out the rotation velocities, and etc. However, in a radial flow, we mainly having an axial fluid getting 90 degrees bend and getting perpendicular to the axis of the rotation, and then still again we do have the same analysis type but different velocity components and maybe different let's say efficiencies. Well, definitely we can have a mixed approach. Well, again, axial fluid could be let's say diverge in an angle plan to the axis of the rotation, and we can have both radial and axial flow velocity components. All right, and the last one, which we're talking about physical action division. Well, impulse turbomachinery. Well, basically we have nozzle section and rotor section, which we are going to explain it more in a next slide. And we're talking about changing the flow direction from the stationary nozzle to the blades, increasing the velocity, pressure change. And this two division is mostly about the level of, pressure change in our turbomachinery device. All right. Now let's have a closer look about axial turbomachinery, their components, and the power generation, let's say, scheme. As you can see in a picture, this is representing a turbine. Well, what we have as a component are statters, rotors, shaft, casing, and covers. What's happening? We have a fluid flows directly into the device in an axial direction, and then statter blades turn the flow so that it is lined up with the turbine blades. So we are just conducting the flow in a correct direction to have the best orientation corresponding to our rotor. And then, since the flow has the energy, it is turning the turbine blades, and then the power is generated and, let's say, transmitted through the shaft output. So this is a 2D model, cross-sectional, let's say, illustration, and you can see where are the statters, how they conduct, and how we, let's say, interacting with the rotor. The configuration in centrifugal turbomachinery, it might be a bit different, and you might have let's say different let's say component, or they name differently. Well, one of them, as you can see, we have centrifugal pump here. We have multiple let's say components such as inducers, collectors, vanes, outlets, impellers, and stuff like this. And what is happening, we have a flow coming directly in axial direction, getting a turn of 90 degrees through the diffuser, and then the rotor is adding the angular velocity and momentum to the fluid and simply conduct it to the exit. So we have we are talking about two different structures. However, there are so many other subcategories and different designs and let's say subdivisions here, but we're trying to talk generally and looking at it. However, based on your let's say application and your industry, you might experience a bit of difference. But this is the general concept on how we're generating power or extracting power from the fluid flow. All right, when anybody wants to do, let's say, turbomachinery design, there are lots of factors can be incorporated in terms of what we want, what is the initial desire and request from your customers, and then you are going for different testing. As one of the stages, we're talking about turbine or turbomachinery mechanical design, but one space going to aero design, the other would be a structural design, and also selection of the material, testing of the performance, and there are definitely some, let's say, measurements you need to do and say it is manufacturable and going further. Now, considering this stage, there are highlights which is coming from detail of mechanical design discipline, like material selection, like flow analysis. In some cases, it could be heat transfer, and when it's coming to a structural analysis side, we're talking about stress, vibration, lifetime analysis, failure mode, maybe possibility of buckling, and everything else. What we're trying to do by all of these tests, either it's thermofluid analysis or a structural analysis, we're trying to achieve higher speeds, higher spool pressure ratios, higher pressure rise per stage, higher aerodynamic loadings, lower spec ratios, higher solidities, and improved configuration and blade shapes. All it is done because we would like to make the best design with the best performance. Now, if you're considering what we have reviewed, there is a method we call conventional design, where you are having empirical methods, well, we have involving a large number of variables to meet the system requirements. And if you're going into that direction, we're almost facing with a very complex, let's say, problem. In some cases, in a 3D form, it's not possible to solve analytically. It is very time consuming and it's required a lot of human effort. And also when it's coming to the verification stage, producing the prototypes could be time consuming as well as very expensive. CFD is a numerical tool. We call it computational fluid dynamics, and definitely it can assist us to make an evaluation, early evaluation about the performance of your design and finding out if there is any flaws in a flow and in your design. You can have quantitative and qualitative measurements of the design parameters, such as flow patterns, pressure drop, torque required, and then based on what you have found, you're going for a comparative studies and find out the best design or optimum design by making your design parameter varied, such as the dimensions, angles, flow types, and etc. Okay. So this power tool can be utilized on turbomachinery specifically, and there is a specific, let's say, application in this area. Now, before we go and explore more about CFD analysis in turbomachinery, let's first define a very basic concept of what is rotating reference frame. Before going for a official definition, just looking at the video is playing at the moment, and imagine there is a disc and there is a ball on a disc being attached by a rope. Now imagine for the first case, if an observer is on the disc and when the disc is rotating, what he might see, because of the forces that is going to move on a straight line. So the fact is, disc, the ball, and observer, all of them are rotating together. And a very complex motion of that ball, as it is a curve motion, as you can see here, if you are stationary and not rotating with the disc, getting simplified to very straight line, let's say, motion. This is called a rotating frame of reference, and this is a technique most of the CFD software are using it and employing it to make the very complex problem of unsteady flow and highly turbulent flow around the blades of turbomachine components into a more steady state, let's say, sort of problem. All right, if we have a closer look to what we said, in all turbomachinery devices, there are parts which is attached to the rotating shaft, and they are rotating as a let's say at certain angular velocities relative to the machine axis. And there are some stationary parts like stutters, casing, inlet, exit, and everything else, but they are not having any motion. Now it depends on us how we would like to treat this problem. You can be a stationary observer and definitely you will see the flow as a very unsteady and let's say fluctuating. Or if we just moving, when I'm saying moving means we have a coordinate system of our calculation being transferred to the axis of the let's say rotation, or let's say put our observer on the rotor. Then we will have much simpler problem, as you can see as a case comparison in these two studies. So as a summary as what we said, on a steady problem with respect to absolute reference frame can become steady respect to the moving reference frame. Complete rotor domain is assumed to be rotating at the same angular velocity of the rotor. Then, since we have transferred our, let's say, reference or coordinate system, the equation of motion are getting modified, and additional acceleration terms such as Coriolis and centripetal acceleration terms will be added, and then we will have an easier steady state problem to look at, which is requiring less time and computational effort. And this is a very, let's say, common practice in all, let's say, industrial applications. Well, there is an exception here. Well, if you have really an unsteady or transient flow problems by its nature and by the inlets and outlets, it's really hard to, establish this scheme. And then what remains important is the synergy of the information between the stationary frame and the moving reference frame. So in both procedure in SolidWorks, we do have a scheme to treat such this problem. So as you know, SolidWorks flow simulation is a wizard-based interface to set up the flow analysis, and you can have three different methods to say there is a rotational region in my turbo machine, and its interaction with the other one are based on, first could be global rotating. Well, the model and the global coordinate system are considered rotating with the specific angular velocity, means we have transferred. And it is well applicable when all non-rotating model components are symmetrical with respect to the selected rotation axis. We're mostly talking about axial flow in, axial flow out. The other one, we might have multiple of these regions, and we would like to focus on setting up multiple of them. That is one of the things. We call this, let's say, scheme as local regions averaging, and we can simulate the fluid flows in a region surrounding rotating solids which are not bodies of the revolution. And the rotor-stutter interaction is big. We have enough gap between these two components. And the flow parameters within the rotating region are calculated using steady-state approach and average on the rotating region boundaries. So we're talking about moving to, let's say, rotating reference frame and transfer our, let's say, coordinates there. The third one, which is the most complicated one, is local regions by sliding. Well, we have unsteady flow, time-dependent flow, And then we would like to make a strong connection between the cells inside the rotating components and the cells outside of it. And we have a strong, let's say, connection or interaction between the rotor and the stutter that might be tiny gaps. All right, so all of these three are the options we have in SolidWorks Turbomachinery, and today we are going to look at how we can, let's say, utilize them if you have a project. The first step we have to, let's say, consider and understand is to make a dummy component. Well, we call it component representing a rotating region. And we have to create them. Imagine the case if you have a room, a fan is mounted to the wall, and you would like to tell the software there is a rotational region around the fan. What you have to do is first to create a component which has some certain, let's say, criteria to meet, put it there, and inside the analysis you have to specify this is the rotating region. So physically creating in a design, let's say, tab, and then become virtual in a simulation tab. This component has some certain criteria to meet. First, the component's axis of revolution must coincide with the rotation axis. Second, it must be fully enclosed by it, and the rotating component walls must not, let's say, contact or intersect the rotating region boundaries. Third, it must be asymmetrical with respect to the rotating component's rotation axis. And next one, it should intersect, its intersection with the other fluid and solid region must be asymmetrical too. And the last thing is if the model includes several rotating solid components having different rotation axes, the rotating region surrounding these components must not intersect with each other. So you can have multiple of these components in a different axis rotation, but there shouldn't be interfaces. So what we found and what we said, a dummy component is going to be physically modeled. It is going around your rotating region and there is no intersection and it's fully aligned with the direction of your rotation. That is the first step we have to take before doing anything else. All right. Now it is the time to look at the case studies by going to the SolidWorks. Let's review what we do first. The first case study we're talking about centrifugal pump assembly local region averaging, let's say, procedure. The case study is considering a pump with impeller, casing, in and out pipes, and the leads to enclose the region. The first case we are considering that it is the impeller is rotating at 1800 RPM. Water inlet and outlet is basically atmospheric, so we have a reservoir and we would like to transfer, let's say, water from one pool to the next pool without having any height difference. So sucking the water from one source, atmospheric pressure, and then discharge it to the other pool, and again atmospheric pressure. So there is no head, and we would like to find what is the discharge rate, and also we can find what is the torque required for this action. In the second case, we're making it one step forward, and we would like to find what sort of head is generated if we have inlet on atmospheric pressure and almost or fully closed the outlet and looking at the head value. This time, again, our impeller is rotating at 1800 RPM as well. And the third case, we are going to increase the RPM to 2400 RPM and again going to examine the same thing. All right, so that is going to be our first case, and the approach we are using is called local region averaging. Means there is no strong interaction between the rotating region and the out cells, and we're simply having a steady state sort of problem. However, SolidWorks capabilities in doing turbomachinery analysis is beyond this point, as in our second case, we are talking about a mixing tank for applesauce and olive oil. Both of them are non-Newtonian liquids. It could be any liquids that's compressible or incompressible. As you can see here, we have a tank with a, let's say, blade to mix. We have an impeller which is rotating at 6 RPM. We are talking about the outer wall as to be stationary and adiabatic, no thermal reaction. However, you have the option to do that. We have 2 inlets, and initially both liquids are inside the tank is around at 333 Kelvin. Applesauce enters at 0.02 meter cube per second at 298 Kelvin, and olive oil enter at 0.01 meter cube per second at 80 Kelvin. And basically, after the mix, both of them are discharging to atmospheric pressure. Alrighty, so these are the 2 case studies, and let's bring our models. Here it is. Alright, having a look, first I would like to go and let's explore what I do have in my design tab. If you have a look, I have made, let's say, an exploded view about the components I have. I have the pump casing, I have the impeller, I have the suction flange, I have the rotating region as a dummy part as we have introduced, and there are 2 leads. Now let's have a closer look. I would like to hide a couple of these components. First here, not the flange, and what I would like to just remain is these 2 components. Make sure I'm doing back on collapse, and interestingly I make a section. Now look guys what I've done. Here it is, and you can see basically what is being created. The impeller is here as the red component, and you can see the dummy region is going around it with some gap. Not a very huge gap. We're talking about something considerable. Alright, around that region. What we are going to tell the software, all the rotations are happening within that dummy face, and maybe the let's say the rotating component inside is the impeller. It's more than important to make no crossing, axial alignments, and put some appropriate gaps remain in your design. Alright, this dummy component may interfere with any of the other solid components you have on the other side. That's not a problem, but it shouldn't have any interferences with that rotating component. Alright, so looking at this one, and we found how we should organize that. Do not waste a lot of space, do not make high clearance and larger gaps, because that could affect your calculation result. Then we understood we have prepared our dummy, let's say, component to be as a representative of our rotation region. Let me switch back everything to the shown state, and let's come out of the section and back to exploded view. Alrighty guys, now it's the time to create the project. As you know, flow simulation is the add-in to your SolidWorks, and definitely you can manage it. If I can get it, okay, add-in list, and you can go to your add-in list and make your flow simulation to be active. When you're coming to that point, in order to create a project, as we said, it's a wizard base. So click on wizard, give it a name, be assigned to any configuration as you might like it, or even create it at this stage. Click next. Deciding about unit system, SI. If you like to make a modification, you can definitely do that. Make it from Kelvin to centigrade, as you might like it, or keep as it is. Then we have the main decision point, as you can see here. The first thing we have to say is what is the analysis type. Internal, a flow inside an enclosure. Well, definitely you need an enclosed region. As you can see, there is a lead coming to that pipe. There is another lead to that pipe. There is no leakage, and we have a volume created. This is called internal. Or if there's a flow over an object, then we call it external. Like you do a testing for in a wind tunnel. There are multiple options you have to say here. One of them is heat conduction if you like to consider radiation options. If you have a steady state or transient, if gravitational effect is active or not, which we have covered almost all of this in the other examples and webinars we had. But what is the main area of interest for today is rotation. And by ticking on that one, you're telling the software, I'm either going for a local region averaging, or I can go for local region sliding. And if you're choosing that one, definitely you need to be time dependent analysis, or we have global rotating. Okay, now it depends on what you want and what is the reality of your case. You can choose one of them. Let's choose local region averaging and then move forward. The next stage we have to take is to say what sort of fluid is working here. Inside the liquids, I can go and have a selection of the water. Always you have the option to define new material, remove what you have selected, add the other ones, and basically go ahead. In this section also you can say what type of flow you have, like laminar, turbulent, both of them, and also you would like to consider cavitation or not. One very important pause I would like to put here, in SolidWorks flow simulation, changing phase or multiple phase is not we can cover. However, based on the density change of the fluid flow, we can decide it might have a cavitation occurred. So this is another topic and we might discuss it later on, but just letting you know, if you're in this, let's say, procedure of doing any turbomachinery design which is considered that fact of the phase change, this is not the appropriate software. But if you don't have this effect, definitely you can have and you can add cavitation at this stage. The next thing, our boundary is adiabatic, means there is no interaction between our boundaries and the surrounding. And also you can specify roughness to all the pipings and the surfaces that you have for your design. And the last thing you have to say about initial condition is about your domain is initially at what sort of condition. Pressure, atmospheric, temperature 20. Is there any predefined velocity or initial velocity in XY direction, or even turbulence parameters here? If you click finish, then what would be happen? You will creating your first project and flow simulation is coming here, and you will end up with getting one simulation project, which we call it no head, and there would be two sections, input data and result section here. And that is exactly where we going to start adding more and more information to the project. So if you have the question of, there are so many things not being answered, like what is the material for my solid if I'm activating conduction? What if I would like to make, let's say, boundary condition here, and how I'm controlling my mesh here? These are the questions. Well, you are going to answer it on input data procedure. By expanding this, we can see the first thing is computational domain, which is an imaginary box where are the calculations are bounding. And the good thing is you can use this option to make the calculation limited to certain components by simply drag and drop, or go and edit definition and making X, Y, Z directions or limitation to be set. Also, you do have the option to go for a symmetrical boundary condition, means there is exactly the same shape on the left side, right side, upside or downside in any direction, or you're saying there is something is going to be repeated, periodicity, and simply telling, all right, I have an impeller with 10 blades, and basically it's fully symmetrical, but what I would like to do, solve it for one and expand it to the other 10 and make a fully symmetrical result. But again, you need to have a symmetrical shape, and your problem needs to be symmetrical as well. Okay? So considering those facts, we're telling where are the limitations or borders of the calculation and CFD region. Now, in order to make let's say our turbomachinery analysis active, we said we have created a dummy or rotating components. What we have to do next is basically going to our rotating region, means either we going to let's say our flow simulation and going to insert and we'll say rotating region. By doing so, you have the option of saying which component is representing the rotating region. Well, basically, we know which one it is. Here it is, rotating region, and give it an angular velocity. So basically, the pump is working at the speed of 1800 RPM. Clicking OK, and you basically told the software there is exactly going to rotate. All right, so we've done this and we told the software about the axis of the rotation and direction of the rotation. All right, now from this point we almost going for the same procedure as we're doing in any other fluid simulation. However, there are some exceptions because we have to make sure we're defining our walls and the behavior of the walls. And either if we'd like to have the rotating component in reality rotating, or just having the dummy region just rotating. That is all can be defined in your boundary condition section. Okay, so by right click on your boundary section, you can insert boundary condition. Well, you can see the first we have is flow opening, either in inlet or outlet, and can be defined as a mass flow rate, volume flow rate, or velocity components. Give it a value, making sure your thermodynamical parameter is being set, such as temperature. You have specified the correct turbulence on this inlet or in this boundary condition. The other type we have is basically the pressure boundary conditions, such as environmental, static, or total pressure with thermodynamical let's say properties, turbulence, and boundary layer properties as well. And the third one, which is very let's say active in our flow simulation in turbomachinery, is the wall condition. You might have your, let's say, components, the dummy components, to be around so many components, including the rotor and stutter. Well, you might choose those, let's say, regions inside the rotating region to act as a real wall with the wall parameters as it is, or even going to say it is on a stutter. So basically you might have an impeller and a casing around the impeller and then the big casing, and you putting your let's say component, the rotating component, including those, all of those, or partially you know, considering both of them. You simply go and tick this is stutter. Let's see what I've done here. I said there is a real wall, and this real wall is considering all my selections, as you can see here. What I'm telling at the moment is, although I've set my dummy region is rotating at 1800 RPM, I don't want to physically rotate these plates. That's what I've selected all of this and said it's real wall, and I haven't get the wall motion to be anything rather than 0. That is one application. However, I can say it's on a stutter and it's not moving. That could include anything inside your rotating components. All right. So the first thing I have done as a boundary condition is basically telling the software I would like to have rotation within this dummy region, but that blade is not physically moving. Okay, and it's a wall. It's physically a wall, so you can't cross the boundaries of solid and fluid altogether. So we're telling the software this is a wall, this is a solid region. All right. Now after that is very basic and back to the normal. We're saying there is a static pressure on the first lead at 20 degrees, 1 bar, and there is another outlet pressure which is again 1 bar, 20 degrees. Means basically the pump is working to suck the water from the first pool and on the same height just discharging it to the second one. All right, as we said, the ultimate goal is basically to find what sort of head we are, what is the discharge rate and what sort of torque required. All right, before we go for a run of this analysis, what we have mentioned, it is more than important to make sure we are capturing all the important events inside our result. And this is highly dependent on the mesh you're generating. Well, basically, you know that when we are doing any CFD or FEA analysis, we're converting the actual CAD geometry to the number of the cells attaching together, and we basically do the R calculation there. More of these cells we have, more like calculation points we have. And less we have, less calculation. Means like in reality, if you just measuring something, you putting a probe at some point or multiple points. More probes you put, better, result you get, more realistic image you get, or like pixels on a picture. But that could be very time consuming if they are very huge. Therefore, we need to make an optimizer. One very common practice, as we said, I came to my dummy region and make some refinements to make sure at least between the gap of this dummy region and the solid component of the, let's say, impeller, there are some 2 or 3 cells as a gap, and the calculations are not getting affected locally and globally. So there are so many, let's say, adjustments I can do by refining the cells in fluid, refining the cells on a partial cells, means exactly the interface of fluid and solids. What we do for narrow channels, what sort of refinement level, and the other factors, as you can see here, small solid feature refinement level, or even curvature, let's say approximately level, making this more to the 9 level or getting back to the 0 level simply means more fine or more coarse mesh we're generating. Finer, better result, time consuming. 0 or 1, very, very coarse mesh, quick answer. Again, what is the best one? That is a simple procedure in all CFD analysis we have to take. We might have 2 comparative studies to find if there is any significant change based on increasing or decreasing number of elements. So as you can see, I have done my measurements on the geometry. I found the gap and I've adjusted my mesh parameter and make sure I've captured everything in a correct way. Then what is remain is to make sure what sort of parameters we would like to trace later on or we would like to analyze. These are basically defined as a set of goals. Goals could be a general or global goal. It could be a point goal, surface goal, volume goal, or an equation goal. Means if you basically select any of these, you will say to the software, total pressure average is what I would like to trace globally. Or if you go and select a surface goal, you will say on this surface I would like to trace the minimum total pressure. So what must be done is there are some parameters you would like to follow up. For instance, you would like to follow up the pressure drop. Then, yes, make a surface goal on this surface, make other surface goal on the other surface of the lid, inlet and outlet, then create an equation goal, say pressure 1 minus pressure 2. That's how you trace the pressure drop. In this case study, let's say, globally we are tracing the average static pressure, as you can see. Next, we are tracing the Z component of the torque on that impeller. In order to find this condition requires how much power. Static pressure on a surface, which is the surface of that lid, and also volume flow rate on that lid. Why? Because we would like to see how much is the discharge. That was the initial question. So I'm just reminding again our initial question: if the impeller is rotating at 1800, how much discharge is happening here and what sort of pressure or head we might achieve. So since we have specified our goals, it's ready to run. So click run, and then you will see the convergence, and after that you can load your result or automatically getting loaded. And now it's the time to look at what we can do and what is the fluid result look like. Alright, so let me load that. Not supported, very bad, so I have to open it in 2015 then. Okay, so let me close this case and do not. Unfortunately, these results are a bit old, and I can load it in our 2015, doesn't really matter. Alright, so let me start it up and load my result. Okay. Okay, I've got my SolidWorks, and let's bring it to the screen, maximize it, and let's browse the document. Here we are. Alrighty, loading that one, go to my flow simulation tab, and basically make sure I'm in no head configuration, loading my result. Okay, result been loaded. Always you have the option to read the result at, after you save the simulation. Now let's have a look, make sure I'm getting this active, and I prefer plain white. Alright, okay, now we finish the first section, which is input data, and now we are in a results section. As you can see, there is a big list. You can have a look by first making cut plots, right click and insert, then say I would like to cut my model based on front plane or any other plane you have here, front, top, or any let's say specific one you have made it, to show the contours, iso lines, vectors, streamlines, or mesh, or even all of them or some of them, and on each of them what needs to be shown: contours of velocity and vectors of velocity, both of them, or streamlines of the velocity. Okay, so all of them are possible to make a cut section. That is the first thing I've done. If I show you my first cut plot, you can see I had an evaluation on this plane, and let me hide the model. This is my velocity profile, and you can see the mesh as well as velocity contours. You can see how refined the mesh is, how many cells you have, and what is the contour of the velocity. All the cut plots definitely can go and make a play and move from one end to the other end. Let me activate the model, and you can see it can be animated and go through the different section, and at any stage if you like you can basically stop it and get back to what you want. You can have multiple of them active and having a look more closer in, you know, closer to a 3D presentation. Well, now we can see what is happening here. Distribution of velocity, contours in a different region. Well, basically we can see the vectors of the velocity as it is averaging on or inside the let's say rotating region, and it's going to be diverged when it's going out of this region and showing more of a realistic view. Again, that could be definitely animated and going at different levels. So this is the first 3D presentation you can see. You can evaluate anything on the surfaces by, again, going to your surface plots and then, surface plots, and making any sort of decision. Like, I would like to know, let me come back and hide these two plots first. That is making it easier. Make sure I do have an exploded view. And then looking at my surface plot, insert, I would like to see the contours of, let's say, pressure on that surface of the casing. If I can select, that would be nice. All right, so let's make it simple. Pressure, click OK, and that is almost a constant pressure is coming out of the pipe. The other option you have is to create isosurfaces, surfaces which has some properties of some value. Like, you can go pressure, there is 3 bars, and I would like to show them here. Click OK, and let me hide this one and show the isosurfaces. Now, if I hide my model in here, these are the regions. Well, I have that much pressure, and it's been highlighted in this color. So either I can have the model here, and you can see it. So as many isosurfaces you like, you can definitely create them. All right. The very important one as a post-processing option is the flow trajectories. Well, you are simply defining streams of the fluid starting from one phase and telling how many seats or points are starting, what they look like, what is the width of that streams, and by clicking OK, you will create the flow trajectories, which is showing what you can see here. Again, let me hide that one, and the good thing is you can always make an animation and looking at the realities of what you have created. Alrighty guys, so that is an inflow rotational region. Definitely you can see it is not crossing the impeller region. Well, the impeller is not physically rotating, and it's showing how the fluid is getting exit. Alright. This is almost about 3D presentation of the result, but in so many cases we would like to know about, let's say, exact values and make a measurement on exact points, surfaces, and etc. Well, as we said before, one of the options and the tools we have is to creating the goals, and later on we trace the goals here. What I've done, I've inserted a goal plot, right click and insert, and you can see I have the list of the goals I have, such as volume flow rate of exit. If I show, I can read that this condition will end up with the average value of minus 0.8633, let's say meter cube per second at that phase. So this is one of the questions being answered. What sort of flow rate we are creating. The good thing about that one, you can export it to your Excel file and later on do any other analysis. Look at the other goal I have created. Here it is, the edit definition, and this is the torque required. For such this condition, we are talking about this average value Newton meter, 4469.02. Newton meter torque required if you have this fluid, if you have such this design, and if you have this boundary condition. Now it's up to you to say yes and going forward for optimization, or saying no, that is not simply telling me what I want, and then I'm going to change my dimensions, my design, and everything else. All right, so goal plots, surface plots, let's say volume plots is all giving you the exact values, or in some cases as a graphs, and you can simply judge the performance of your design by them. So you have two options, a 3D presentation of the result or parameter, let's say, evaluation. Alrighty guys, so we have answered the first question. Let's move to the second question and say, if we're closing the outlet, make it almost zero volume flow rate, what sort of head we are generating? That is the same project, which is simply being duplicated or columned. And then what I've done in this project, I've made a change. First of all, what I've said, same real wall, static pressure 1 bar, and you can see what I've changed here. 1 E minus 6 meter cube per second. You can't put 0, but this is a very, very small, for let's say, outlet flow rate. Now, the same thing as I'm measuring, defining the goal, local initial mesh, and basically loading the results. And what we can evaluate here is very important for us. Same plots and same things we can see. For example, if I show that, and I'm showing the other one on here in both directions, and then you can see third one as going more and more in detail, and you can see there is no exit pressure and mostly being pressurized the let's say piping area and the casing area. Now, what else we would like to check is the goal plots. Edit definition. I'm checking my component of the torque, and it is now telling me it is 3353.96 Newton meter, and the main question of how much head is here. So edit definition, I'm asking about static pressure of the outlet, and it is basically having an average of 26 bar creating. That is telling you, or can be easily converted to the head, and you can see if this device or this component is maintaining the design goal of your project. Similarly, I've done the same thing. Well, I've basically made my rotation speed to reach 2400 RPM, and with the same condition as static pressure, outlet volume flow rate of nearly 0, static pressure in, and real wall condition, I basically achieve the new one of static average pressure. Sorry, I had just forgot to load the results. That is my mistake, sorry. So first load the results, and then looking at my goal plot. So the goal plot is showing me this time in the average 37 bars on the outlet. So this is a design trend, and I can see if I'm making the rotation more or less, am I reaching to what I want or not? That is the first thing we might have a look as a design optimization. However, in SolidWorks you have more and more options to make a new parametric studies, and then in new parametric studies telling what needs to be varied as a simulation parameter. For example, you're doing the rotating region and basically selecting the angular velocity and say yes. And then from this point, you're saying how would like to change it. For example, we would like to say it is changing range with the step from minus 1000 step to 5400, as the step size is every, let's say 100 RPM. And hang on a minute, oh yeah, so let's reverse it. So because it's minus, I have to change this. Alright, so let's do this as minus 1000 and click OK. Alright, these are the scenarios, as many as I like, I have created. Also, I can make a dimension selected for my analysis. Well, if I have marked anything, these are all look like imported, and okay, yeah, here it is. I found one of them. Like this 700 mil is what I would like to make the variation, and basically my variation scheme is again range with step from 0.7 to 1.7 every 0.1 meter. That is okay, sorry, 0.8 and make it 0.0. Sorry, my apologies. All right, so this is dimensional, and then these are my input variable. My output parameters is my trace to outlet pressure and also the torque required. What is happening, then I have all these scenarios. Well, you can see how many scenarios I have created. All right, these are all the scenarios of 495 scenarios. Well, it is going to update your model automatically, changing the values of RPM, changing the values of dimension, and basically giving you the answer comparatively here to looking at the values of your goals, and you can export it to Excel after the run is finished. Well, it's very ideal to set it for weekend run and coming back, compare and see what is the best one. Alrighty, so that is almost finishing our let's say first case study, and now let's have a look to our second case study, which we're talking about incompressible float and a sliding mesh option. And we are not going to solve it, we are going to just have a quick review about what we have, and then we go for the video of it. Where is it? Here, yeah. This is mixer 2, which I don't want it. No. Let me open up the correct model, do not save, and let's browse. We need the mixer one, which is not here. Fine, I'm going to open it up. Okay, flow simulation, and going to sliding mesh and thermal mixer. Okay. Here it is. Here it is. Okay. Now, look guys, I have two projects defined in this configuration. One is a bit the smaller step, making more refined sort of outputs, and the first one is basically a bit coarse. My project, let me hide my mesh here. Where is it? Okay, basic mesh, hide basic mesh. What I have as a cross-sectional, we can basically see what we have here on this one. Yeah. So you can see the impeller, the rotating axis, and everything else. What I've done, I've said, first of all, if I go to my general setting, I have time dependent, and my rotation is now local region sliding means strong coupling between the cells in a rotating region and the cells out of it. Then we have the fluid. As you can see, there is a water. There is apple sauce, which is non-Newtonian fluid, and there is olive oil, which is also non-Newtonian. So it has been selected from that material, let's say, library, or if you don't see what you want, you can definitely create. Wall condition and initial condition. All right, so that is done. And basically the same concept. Rotating region, yes, that is the angular velocity. Second, real wall, where it's not rotating. So I said yes, inside those faces are all Stutter. Now you have the option to activate the temperature or not. Now in my subdomain, what I've said, where is its boundary, what is inside it, apple sauce and olive, what is its initial condition, and now you can see 333 Kelvin at 1 kilopascal. Then I have my inlets. Environmental pressure, apple sauce inlet, well, you can see that is the face of the lead. Inlet volume flow 0.02, and when you have multiple selection of the fluid, you have to tell the mass fraction. Apple sauce 100%, olive oil 0. Similar to the other side. Olive oil, that is the inlet volume flow rate, and this is the fractions. All right, the rest is talking about what we have defined as the goals, what we would like to trace, make sure our initial mesh is fine enough to capture everything between the gaps and the, let's say, correct results. And basically I can show you what is happening here if you running it. So it is showing us that the first flow, let me make that one to repeating. Two flows are coming, how they mixing and how this is getting developed. Alrighty guys, so basically what we have covered and what we have showed, you can have thermal condition, you can have sliding mesh, you can have averaging, let's say, scheme, and you can have the rotation of the blades as well as not having them, and update your, let's say, mesh and the flow region more. One thing for sure guys, the second approach, which is this one, and it's sliding, is definitely more and more time consuming. It depends on the, let's say, project size and the domain geometry. It can take from hours to days or weeks even. So it's very important to understand what you want to achieve, what you have to simplify and make sure that your mesh is all optimized. Alrighty guys. Last but not least, this is flow simulation capabilities. You can do rotating, let's say, components on the entry license, which is flow simulation. However, this flow simulation capability is not limited to what you can see here. You can add electric cooling module if you're in that business, and if you are in the business of HVAC as well, well, that is a combination about what we saw here is another one. If you have any sales inquiry about flow simulation product, please make sure you're contacting John Belsham, or if you have any technical information or more presentation, more in-depth presentation required, please contact me, Spandiar Kuhi at intercat.com.au.